This is a lecture on logarithms for Math 107, Chapter 4. It may be a review or an introduction depending on your background. The logarithm is the inverse of the exponential. It's a function that is the inverse of the functions, the exponential functions. But it's not the inverse taken in an algebraic way. Instead, it is the inverse taken in the graphical way. So what I'm showing here are several exponential curves. The blue one is e to the x, the green one is 10 to the x, the two red ones, this red one right here is 2 to the x, and this red one over here is 3 to the x. Now to take the inverse of a function, you draw this dashed line, the diagonal line, which is y equals x, and then you reflect that curve about the diagonal line. So you folded the paper along the diagonal line and trace through to produce the other curve. The inverses for e to the x and 10 to the x are the only ones I show, and that there's a reason for that. So here's it's called the natural log of x. It's the inverse of e to the x. And the other one, log x, is the inverse of 10 to the x. I could have drawn the others 2 to the x and 3 to the x, and I could have drawn those inverses also, but they would just make it more complicated, and actually in practice you don't use them. So I didn't include them. So every time you take an exponential and you reflect it about that diagonal line, you get another curve. You see, they aren't all the same. And you have to make a specification of which exponential created that logarithmic curve. And that's done by putting subscripts. I'll explain this notation on the next slide. But if I had taken 2 to the x here and I reflected it about that axis, about the diagonal, then I would have drawn, so I had 2 to the x, I would have drawn the curve log, but I'd have to remember where it came from, so I put a little 2 down here. If I did the same with 3 to the x, I have to remember where it came from, and I put log to the base 3 of x. Another way to think of how to draw these curves is that you have xy pairs associated with 3 to the x. For example, you have this point here, which is the point x of 0, y of 1. To create the logarithmic curve, you take those values and you write them in the opposite order. So 0, 1 will become 1, 0. And that's done for all the points along the curve. Now I will explain the notation that I use for the log to the base 10 and log to the base e. So in a formal way, if I have an exponential curve with a base of 10, then its inverse is log, and I have to put a little 10 down here, of x. If it's e to the x, then my inverse is log to the base e of x. That's a formal way to write it, and that's written here and here. Those are the two that you use in practice. They are the two that appear on your calculator and also in computer programming. Log to the base 2, log to the base 3, log to the base 5. There's ways around all that, and you can actually just using those two is fine. In fact, you could use just one, but it's common practice to use those two. There's certain calculators that do not include log to the base 10. Those are some business calculators because they're only looking at interest, and that's why they need the log to the base e, and they don't have the log to the base 10 on them. But all scientific calculators have both. So now we have these two, log to the base 10, log to the base e, and those involve little subscripts on the log, and nobody likes writing those. They're very difficult to do, and in the olden days when you had to type things on manual typewriters or even electric typewriters, you had to release that roller, then try to shift those pages, and there could be several papers all with carbon paper between them, and you'd have to kind of roll that up. Then you'd have to type in that one little subscript you wanted, the 10 or the e. Then you'd have to try to get all those papers to go back to the original alignment, and then lock that roller and go on, and many times it did not work. So one way to avoid things is just simply not to do them, or one way to avoid problems, simply not to get around what you were doing. Here's what we do here. I think I didn't say that in any kind of straightforward way. Okay, in order not to have to write subscripts, or to make that subscript writing easier, we simply get rid of the subscripts. There, that's a little better. Okay, so how do you get rid of them? You have to have a different abbreviation for log, when we mean log to the base 10 or log to the base e, to distinguish between them. The custom practice is to write log with no subscript, and that is understood to be base 10. So if you just have log of 2, that is understood to be log to the base 10 of 2, and no other logarithm. The 2 here is just the argument of log. For log to the base e, it's abbreviated ln. Some people say natural log, or it's Napier log, and that means anytime you say ln of any number, say ln of 5.5, that's understood to be log to the base e of 5.5. So those are two abbreviations that are fairly standard, and you need to know these ln and log with no subscript and what they mean. In the computer world, they're fairly universal. Some programs don't really adhere to this. There's one graphing program I use that doesn't use this abbreviation. So you have to check when you're programming, and in the language that you're programming, what the abbreviations are for log to the base 10 and log to the base e. It might not be this exactly. Now, having said all that, the screen has an error on it. I wanted to show you the important values for logarithms. Because logs are the inverses of exponentials, they inherit in an inverse sort of way certain values, and they also inherit certain rules. Again, things are inverted, and some stand out as having particular importance. Here is the general idea, and here I'm crossing this off because I violated my own spiel about the abbreviations for logs. If I have an equation y equals e to the x, here's the y, that's my answer in this exponential equation involving e to the x. Now, if I take the natural log, I have to team it up with the e, so I'm going to use natural log, but in this case I'm going to take natural log of the answer, then I will get the exponent. So this was that exponent, and here was the answer. The same thing happens if I have an equation like this, y equals 10 to the x. Then if I take the log of the answer y, I will get the exponent x. Let's see how that works. And these are the important values, and this also demonstrates that rule. 10 to the 0 is 1. If I take the log of 1, I'm going to get the 0, because the 0 was the exponent. So here's the answer in the equation. I take the log of that answer, and I get the exponent. For the next one, again, the exponent is 0, and the answer is 1, because anything raised to the 0 power is 1. So the correspondence here is natural log of 1 equals 0. This is universally true. The natural log, or the log of 1, is always 0. Just like any number raised to a 0 exponent is 1. You can kind of see how these are inverted. But these are two important rules right here, which is really only one rule. Now, if you raise a number to the first power, you just get its value back. So here's where the exponent is 1. The answer is the base. If you take log of 10, that means you're taking the log of a number that is the base, is the same as the base, then the answer will be 1. So what we have here is log to the base 10 of 10 equals 1. These are the same. Now we see the same situation here. E to the 1 is e, log of e is 1. That's because what we're taking here is log to the base e of e. These are the same. The answer is 1. Here are some important rules for logarithms. If you take the log of any number, b is going to be any base, and it has an exponent associated with it, that exponent goes out in front and multiplies, and it multiplies the log. So if I have log of 16 to the 9th, that is 9 times the log of 16. So what's the log of 16? You can try to work it out by using some other rules, or you can use your calculator at that point. You also could take 16 to the 9th and try to take the logarithm. That would be a fairly big number, but the rule is, and this is what we use for simplification, is 9 times the log of 16. If I have some number out here like 3 times the log of 16 to the 9, when that 9 comes out in front, it's a multiplier, so you get 9 times 2, which is 27 times the log of 16. And this holds, of course, for all logs. Natural log of 3 to the 4th is 4 times the natural log of 3. That's a very handy rule. And here's some examples. Log of 10 to the 6th, the 6 comes out in front, and then you have log 10. This is particularly good, and you like the situation because what is the log of 10? It's 1. This is a value 1, so the whole answer is 6. Now if the exponent is some expression like 2x plus 6 here, that whole thing comes out in front and is a multiplier of log 7. And log 7 is now a button on your calculator, and you can work that out. Natural log of 25 to the 9, the 9 comes out in front. These are just examples with natural log. And here we have natural log of e raised to the 95th power. The 95 comes out in front, but natural log of e is 1, so the whole answer here is 95. If the argument of a logarithm consists of two terms multiplied together, a times b, that breaks out into log of a plus the log of b. This simplifies your calculation, but first I want to show you what this is not. If I have the log of a times the log of b, these are two logs multiplying each other, that is not equal to the log of a plus the log of b. This only works when the argument of the log is two things multiplied together, two terms. I've given you some examples here. I'll give you one with some x's too. Here's a log of 60. I could write 60 as 2 times 3 times 10. So I can break this out into the log of 2 plus the log of 3 plus the log of 10. There's a lot of this kind of work was done in the past when we didn't have calculators. Now you just hit log 60 on your calculator and there you go. Also in the past we knew some logarithms in our minds, just sort of by heart. Log 2 is 0.3010. Log 3 is 0.4771, so if you happen to know those, that helps. And then log of 10, of course, is 1. You could add all those up, and you would find the log of 60. So just by knowing a few logs, basically the numbers 1 through 9, and then using this rule, you can find the logs of other numbers. Here's a natural log of 24. Okay, 24 you could write as 4 times 6, or 3 times 8. So I've got 4 times, well 6 is 2 times 3 of course. So this 8 is really 2 to the 3rd times 3. Then I can break these two pieces up into the log of 2 to the 3 plus the log of 3. The 3 comes out in front, so I'm using that first rule, and it multiplies the natural log of 2. So this would be 3 times 0.3010, if you happen to know that, plus the natural log of 3, which is 0.4771. You are not required to memorize the values of logarithms. I'm just quoting some here for you. Along with that rule is this one, that if you have the log of a over b dividing, then this breaks out as subtraction. It's really just a corollary to this rule, because of log a over b is the same as log of a times b to the minus 1. Let me work that out. I'll show you. I have to erase the screen. Get the pin back. Okay. So if I have the log of a over b, that's the same as log of a times b to the minus 1, correct? Now, by the multiplication rule, you can write this as the log of a, fine, plus the log of b to the minus 1. Now, using the exponent rule, the exponent comes out in front, so the minus 1 coming in front is minus the log of b, minus 1 times the log of b, and that's your subtraction rule, log a minus the log of b. Because this is an inherited rule from the multiplication rule, and using the exponent, it has a result when you have two terms down here in the denominator. You get this result that looks wrong initially. If I have the log of a over b times c, this is the log of a minus the log of b minus the log of c. And that surely looks like something was wrong there. The reason that's okay is because this is really the log of a times b to the minus 1, c to the minus 1. So if you use the multiplication rule, you have the log of a plus the log of b to the minus 1 plus the log of c to the minus 1. Those negative signs come out in front. You get minus the log of b minus the log of c. One way to get more familiar with logarithms and their curves is just to look at some important values. What I've drawn here is log. This is log to the base 10. So we're taking log to the base 10 of 1, and we get 0. We get 0 because all logs of 1 are 0. You can't really see that that's really 1 because the scale is going out to 1,000, but that's really x of 1 and y of 0. And of course, you're never really hitting this y-axis. It's just because the scale put that red curve so close to the axis that you can't differentiate it. But I wanted to show more of the curve, so that's why it looks like that. All right, now, the next rule, or important value, of course, was log to the base 10 of 10. I'm writing the 10 just for emphasis because these numbers are the same. The answer is 1, and that's this point right here. So logarithmic curve hits 1 when you take in a logarithm of its base. Now, when does logarithm achieve the value of 2? When you have squared your base. For example, what we've shown here, log of 100 is the log of 10 squared. Well, the 2 comes out in front by the exponent rule. And I know that log of 10 is 1, so the answer is 2. You see, log of 100 is 10 squared. The 2 comes out in front, and you get 2. Taking the log of 1,000, 1,000 is 10 cubed. The 3 comes out in front, and log of 10 is 1, so the answer is 3. That's when they talk about a log scale, that you have to, while the log only moves by 1, the argument has a higher exponent. For example, if your base is 10, to move by 1, you have to multiply your argument by 10. Let's look at natural logs. We're going to see the same situation over here. So natural log, of course, of x is really log to the base e of x. This point is universal. Any log of 1 is equal to 0. You can see this one a little bit here because I only have to go out to 60 with this scale. The other one I was going to 1,000. Now the natural log of e is 1 because when you take the natural log, the log to the base e of e is 1 because you're taking the log of the base. When those numbers are the same, the answer is 1, and that's why we see this point right here. So this at this point, x has a value of e, which is 2.71828. On and on, but that's good enough abbreviation right there for e. Okay, now if you have e squared, which is 7.389, then the 2 comes out in front, then you use this result, natural log of e is 1, and the whole answer is 2. Taking the log of e cubed, the result is 3. Taking the log of e to the 4th is 4. In the next lectures, I'll talk about using logarithms to solve inverse problems, and there will also be a lecture on some physical processes that are described by logs independent of exponents. They just behave in what's called a logarithmic manner.